Hello everyone and welcome back to Teach Astronomy. My name's Victoria, but you can call me Vicky. And today is Monday, which means that we have some book chat coming at you. So I know last week we didn't get to read any because last week was chaotic, and the week before we rushed through a whole chapter. So this week we're just gonna chill. We're gonna do half a chapter because this chapter is kind of long, and we're gonna have a good time. I have no time limit today, so we're gonna go through about half a chapter, and we can chat in between and hang out. Yeah, we're just gonna chill. Monday Fun Day Book Day, yeah. So today's chapter is all about Spitzer, which I feel like for the last few chapters I've been saying this for all of them, but like I don't know a lot about Spitzer. So I'm excited to learn about it. And yeah, I hope everyone's weekend was good. Mine was busy but good. Hope everyone's day has been going well so far, and I guess we will just jump right into it. My starting soon screen is still on. How do you mean? Is it... Wait, you can hear me, but it's not, Is my picture not there? No, okay, Lynn Jersey sees me. In the background. Oh, you mean the stars? Because the stars are supposed to be there. That's just a static background. I don't know. I'm confused. I think people can see me. Maybe CJ SideQuest's internet's a little slow. Oh, the video was frozen. That's so weird. Oh, that's very strange. Well, I'm glad it fixed itself. And I guess we'll get started. All right, so Spitzer, unveiling the cool cosmos. Space is mostly empty, but a thin gruel of gas and dust that occupies regions between stars dims and reddens light. 1,000 trillion mile wide clouds containing gas and microscopic dust grains absorb and attenuate visible light and re-radiate it at an infrared wavelength. NASA's Spitzer Space Telescope has the remarkable ability to see through interstellar dust and has allowed us to look into the vast clouds in which stars are born, like those of the Orion Nebula, our nearest star-forming region. Spitzer can also peer into the dark, dust-strewn plain of our Milky Way galaxy that previously had been nearly impossible to penetrate. Anything that radiates heat, such as living bodies, and any cool object in space, such as planets or moons, or even tiny silicate, rocky, and carbon, sooty grains, 1/10,000th to 1/100th of a millimeter across, emits infrared radiation. Only an infrared telescope can image objects that glow in light waves too long for the human eye to see. The Spitzer Space Telescope can detect such light billions of light years from Earth, and has revealed this cool and invisible universe with unprecedented clarity. With more than 1,000 exoplanets known as of late 2015 and another 4,600 candidate planets identified by the Kepler telescope, astronomers estimate that there are at least 100 billion exoplanets in the Milky Way galaxy. Scientists calculate that 500 million of those planets orbit in the habitable zone, the distance from their star that could allow for life. NASA's Spitzer Space Telescope is helping to detect and characterize these extrasolar worlds. In December 2010, Spitzer discovered the first carbon-rich exoplanet, named WASP-12b, the geology of which may be comprised largely of diamond and graphite. Whereas rocks on Earth generally consist of silicon and oxygen in the form of quartz and feldspar, Spitzer's observations suggest that WASP-12b, about 1,200 light-years from here, has nothing like terrestrial geology. Astronomer Mark Kuchner of NASA Goddard Space Flight Center, who has helped theorize carbon-rich planets, explains that increased carbon in a planet's composition can entirely alter its geology. Quote, "If something like this had happened on Earth, your expensive engagement ring would be made of glass, which would be rare, and the mountains would all be made of diamonds." End quote. Spitzer has been instrumental in analyzing the geological makeup of exoplanets, and what astronomers are finding exceeds their wildest expectations. At the other extreme, from the dim worlds in the nearby universe, Spitzer has discovered massive galaxies billions of light years away that are foraging stars at a prodigious rate. An infrared bright star-forming galaxy might be making thousands of stars each year compared to a couple for the Milky Way. These starburst galaxies are infrared beacons from the early construction phase of the universe, during which many large galaxies were being assembled from smaller galaxy pieces for the first time. Deep within the dust-obscured hearts of distant galaxies, new worlds were being forged at a fantastic rate. A single modest-sized telescope in space has seen directly into the center of these galaxies and provided insights on the full range of their creation stories. That's the end of that section. It's scary. Ooh, yeah. I know one streamer, very different from what we do, but a gem. If you like horror games or fun people in general, there's a streamer called Granny, and she plays a lot of horror games, things like that. But she's a great person. She's a little wonderful little light here on Twitch, and she does this thing where during her starting screen, she'll turn on her audio, and she like you can't see her yet, and it's very weird. It's surreal. And I was just pulling a Granny there, just for CJ side quest though. All right. If you guys actually, speaking of which, I know a lot of people here are we have some people from Twitch that found us through Twitch. We have a lot of people that followed us from YouTube to Twitch, or like from Coursera to Twitch. If you are either new to Twitch or have been on Twitch for a long time, but you watch other people, let me know who you watch, whether like in or out of our astronomy and science sphere. I'd love to know what else you guys gravitate towards, because I don't know, I'm thinking about doing some gaming content one day, because my schedule's all over the place and we're trying to figure out what works when and stuff, but it's a thought. So let me know if you watch anyone else, and I will continue. Working with the palette of light. We inhabit a physical universe filled with electromagnetic radiation spanning a factor of trillions in wavelength. The human eye sees only a sliver of this radiation, designated as visible light. It's as if there was a full piano keyboard in front of us with 88 keys, and we are restricted to making music with 2 adjacent keys or notes. Space telescopes like Spitzer and the Chandra X-ray Observatory, covered in the next chapter, have opened up the palette of sensation and given us an octave or more with which to view the universe. Infrared astronomy in particular has been instrumental in revealing how stars and their planetary systems form. Spitzer can see through the vast clouds of dust, within which myriad stars are being born, and can penetrate the granular torus or dense disk that typically surround newborn stars. This capability has literally opened people's eyes to the worlds that lie beyond the red end of the rainbow. Isaac Newton first identified the colors of the visible spectrum by observing sunlight pass through a glass prism. William Herschel later investigated temperatures associated with each color of visible light. Having in 1781 discovered Uranus, the first new planet since antiquity, Herschel was already the greatest astronomer of his age when he began experimenting with light. He noticed that heat passed through the various colored filters used to observe the sun and carried out experiments to understand this phenomenon. Using a thermometer with a soot-blackened bulb to better absorb heat, Herschel measured the temperature of each color band of visible light and noticed that the temperature increased from the violet to the red end of the visible spectrum. Surprised to record the highest temperatures beyond the edge of the red band, Herschel realized that electromagnetic radiation existed in wavelengths we can't see. He had detected infrared light. Such early discoveries regarding the electromagnetic spectrum paved the way for remarkable new possibilities in studying the universe. Light is conventionally subdivided by wavelength into radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma ray, with radio designating cool, long wavelengths, and gamma rays representing the highest energy, short wavelengths. These subdivisions are merely convenient demarcations for differences along a continuum of electromagnetic radiation. While most forms of radiation can't reach the ground from sources in space, all forms of electromagnetic radiation, from radio to gamma rays, travel at the same speed as light in a vacuum, approximately 300,000 kilometers per second, or 186,000 miles per second. We're intimately familiar with most of these bands of radiation. Radio waves transmit music and news on your favorite radio station. Microwaves make possible communication technologies, including cell phones and, of course, in microwave ovens. Ultraviolet radiation can quickly give you a suntan or sunburn, and is the means by which our bodies produce vitamin D. We became familiar with UV light from the 1970s blacklights. X-rays have been invaluable in medical and dental practice, as well as in fluoroscopy, which offers real-time views through living tissue, while high-energy lasers are used in brain and eye surgery and other delicate medical procedures. Radiation at infrared wavelengths also has powerful therapeutic effects. Low-level cold laser therapy contributes to the healing of wounds, as noted in a report cited by the National Center for Biotechnology Information. A near-infrared light-emitting diode developed by NASA has been used to heal and reduce pain for chemotherapy patients who subsequently suffer from mouth lesions. In the past 50 years, we've harnessed this invisible radiation to vastly improve our lives. And I have a little chart to show you guys. Let me pull that up. There we go. This is from the book. As you can tell, I just took a picture of the book today. But this is a little graph that shows the electromagnetic spectrum. As it says here, the electromagnetic spectrum spans 15 orders of magnitude, from meter-length radio waves to gamma rays the size of an atomic nucleus. Only radio waves, microwaves, and a small slice of optical and near-infrared radiation can reach the ground from space. So, we've got these long wavelength radio waves that are blocked. So the atmospheric opacity is what is being blocked. So if it's up high here, then it's not visible to us. Then these are regular length radio waves that we can observe. That's why we have radio telescopes on Earth. And then most of the infrared spectrum is absorbed by atmospheric gases and is best observed from space, which is why we've got space telescopes and things. And there are dips in places where we can see things a little bit better. And obviously there's a lot of dip in the visible light part of the spectrum, but it's actually not zero because of the atmospheric distortion, whereas radio waves are zero because they do not get distorted by the atmosphere, which is interesting. And then everything higher than that, gamma rays, X-rays, ultraviolet light, is blocked. So yeah, cool stuff. All right. So, the emergence of infrared astronomy. The Earth and its atmosphere emit infrared radiation in all directions, swamping any signals from space. It's analogous to trying to see stars in the noontime sky. For a faint, cool source to stand out against a warmer backdrop, an infrared telescope must lower thermal backgrounds. Which is to say, the longer the wavelength of light being observed, the colder a telescope and its detector need to be to see an infrared source from space. By the 1960s, infrared astronomy took off with the development of a new type of solid-state detector that had greater sensitivity than old-style radiometers. Another obstacle to detecting infrared radiation from cosmic sources is the fact that those waves are absorbed by water vapor in the air we breathe. Astronomers initially chose high mountain tops for their observations, to be above as much of the infrared absorbing atmosphere as possible. For example, Some of the best infrared observations are made 4,200 meters high atop of the dormant volcano Mauna Kea in Hawaii. And new telescopes are being constructed in the arid Atacama Desert in Chile, including a major new millimeter array on the Changnator Plateau at an altitude of 5,000 meters. An extreme version of this strategy was the Kuiper Airborne Observatory, which operated from 1974 to 1995. This 36-inch telescope in a converted Air Force C-141 jet made observations for a few hours at a time at an altitude of 45,000 feet. The successor to this facility is a 2.5-meter telescope in a converted Boeing 747-SP, the Stratospheric Observatory for Infrared Astronomy. High-altitude balloons and rockets carrying small telescopes have been used to reach even higher altitudes of over 100,000 feet. It proved essential to cool infrared telescope detectors to liquid nitrogen or even liquid helium temperatures, so that radiation from the detector wouldn't wash out signals from the sky. On ground-based telescopes observing the near-infrared, 2 to 6 times the wavelength of visible light, liquid nitrogen is used to cool the detector to 77 Kelvin, or negative 177 degrees Celsius. Though seemingly exotic, liquid nitrogen is basically liquefied air and costs no more than milk. For observing at the mid-infrared, 20 to 200 times the wavelength of visible light, liquid helium is used to cool the detector to 4.2 Kelvin, or negative 269 degrees Celsius, a hair's breadth from absolute cold. But the Earth environment emits so much radiation at these wavelengths that astronomical signals are swamped by background radiation, and deep mid-infrared observations can only be made from space. Space infrared astronomy was kicked into gear with the very successful NASA Infrared Astronomical Satellite, IRAS, which in 1983 surveyed the entire sky in the infrared for the first time. In less than a year, IRAS detected about 350,000 infrared sources. Around the same time, ESA launched the Infrared Space Observatory, which had higher sensitivity and much broader wavelength coverage. In 1997, an infrared camera was added to the instrument suite of the Hubble Space Telescope. This camera has been very successful, but it has a small field of view and shares time with 4 other instruments, so infrared astronomers had always planned for their own facility. Spitzer, from its earliest inception, was especially designed for infrared astronomy and is sensitive enough to detect infrared signatures of stars and galaxies billions of light years away. The Space Telescope has been instrumental in unveiling small, dim objects, like dwarf stars and exoplanets, and can even determine the temperature of their slender atmospheres. Originally proposed in the late 1970s as NASA's Space Infrared Telescope facility, the Spitzer Space Telescope suffered from uncertainty, a delay after the loss of the Space Shuttle Challenger, near cancellation, congressional limbo, budget cuts, and de-scoping. Nevertheless, in 2003, the telescope was finally launched, after being renamed subsequent to a public opinion poll conducted by NASA. The last of NASA's 4 great observatories, the $800 million telescope was named after Lyman Spitzer, an early advocate of the importance of orbital telescopes. After launch, the spacecraft took about 40 days to cool to its operating temperature of 5 Kelvin. Once cooled, it took just an ounce of liquid helium per day to maintain the detectors at their operating temperature. A solar panel facing the sun serves to gather power and protect the telescope from radiation. On the anti-solar side, a series of concentric shells and a black shield radiate heat into space. Spitzer's most precious resource was its liquid helium, used to cool the telescope and its instruments to a phenomenal temperature of just 1.2 Kelvin, within an iota of the temperature where atoms and molecules have no motion. This extra cold relative to the liquid helium operating temperature comes from venting the helium into the vacuum of space, much as your skin would cool if a liquid evaporated from it. Background radiation is reduced by a factor of 1,000,000 relative to a similar-sized telescope on the Earth's surface. The telescope's cryostat held 350 liters at launch, as much as the gas tank of a large minivan. Helium evaporates and is boiled away by tiny heat inputs from the instruments and from the telescope structure, so the act of observing steadily depletes this cryogen. The goal of cooling the telescope and preserving the liquid helium as long as possible dictated the telescope's orbit and design. Careful design minimized these heat inputs, which are typically measured in milliwatts. As a reference, your fingertip radiates 25 milliwatts. The Spitzer facility is 4.5 meters tall and 2.1 meters in diameter, and weighs about as much as a minivan. Previous space observatories had used either a low Earth orbit to be serviceable by the space shuttle, such as the Hubble Space Telescope, or high Earth orbit with a period of 1 to 2 days, like the Chandra X-ray Observatory. Spitzer is in an unusual Earth-trailing solar orbit. The big benefit is in escaping from the Earth's heat and being situated in a good thermal environment where the telescope can cool in the vacuum of space. The orbit also avoids the Earth's radiation belts, and there's excellent efficiency of observing because the Earth and Moon rarely intervene. But one disadvantage is that Spitzer's radio signals are getting weaker as it moves away from Earth. Spitzer slips away from Earth at about 10 million miles per year, and is now farther away than the Sun. Only the huge 70-meter dishes of the Deep Space Network are sensitive enough to gather its precious data. Mission planners estimate that they will lose touch with Spitzer by the end of the decade. And that's the end of that section. And unfortunately, I think the end of the decade for this book already happened, because I think this was published in 2013. But this is the third printing. Oh no, maybe it is 2013. Let me find out. Hello, Parzival. How you doing? We're doing all right today. We're learning about Spitzer. Spitzer Space Telescope. I'm going to find out if it's dead yet or not. Are we going to have a eulogy? Let's find out. It's dead. I think it's dead. Oh no, so sad. Oh yeah. Just sad. January, actually, of last year. January 2020. Ingenuity has taken flight. Yes, Parzival, thank you for reminding me. I was going to mention that. If you guys haven't seen, it was all over the news today. I go on Reddit a lot, and I opened Reddit this morning, and like every other news post on different Reddits was Ingenuity has taken flight. So yes, rip Spitzer. poor Spitzer, but yay Ingenuity. We will talk about that extensively on Wednesday. It is a Wright brothers accomplishment esque thing. Yeah, it's really cool. So if you guys didn't hear, on Mars, Perseverance has a little helicopter buddy that he brought with him called Ingenuity, and Ingenuity has taken flight, which is a huge deal because that is the first powered flight on another planet ever. And it's really important because it's not as easy to fly something like that on a different planet because of a super thin atmosphere on Mars versus our atmosphere is a lot thicker. And that's how planes work and stuff and helicopters. So it's very exciting. And we will talk about that a lot on Wednesday. I guarantee you. That's going to be a fun stream. Watch the video and stuff, because I don't know if the videos came in yet, but they're supposed to be. I'm pretty sure Perseverance took video of Ingenuity. It was supposed to, and Ingenuity probably took its own video, or at least some pictures or something. So that should be really cool to look at. What happened to Spitzer? We'll probably find out at the end of this chapter, but I think it just actually I can show you guys this. This is pretty cool. So like it said, the Spitzer Space Telescope was slipping farther away from Earth's orbit every like, what was it? 100? How many miles? 10 million miles a year. So it's pretty big. So it's it's the chapter that we're reading today. But it was deemed, done. The mission was finished at the end of or at the in January of last year, which honestly, like, it was supposed to last for, let's see, the planned primary mission was going to be 5 years. 2.5 to 5 years. The primary mission was 5 years. And then it continued on for another 11 years to do research. So it had a good life. But this is what the this is the Spitzer Space Telescope's orbit. As you see, it continues to get farther away. So she's still up there. It's just that the data can't get back to Earth anymore. So she's hanging out in space. It was a good scope. You want to buy a NASA card because the stuff they build lasts so much longer than it should, right? They need to, yeah. Yeah, it was retired in 2020. They retired, the mission ended, yeah, stuff like that. It was just, it says here, yeah, it was limited in the end of its life. We might get to this in the chapter, but the communications, because of how far away it was from the sun, the communications were limited to only like a couple hours a day. It could actually send information because the battery was just not filling up enough, and it was retired after that because they just couldn't reliably get data from it anymore because it was so far away. But yeah, it's still up there. All right, let's continue. I wonder if NASA has a ceremony for the ending of a mission. I wonder if they do. They must, right? Or at least it might not be like a public thing, the way that they do, like, their live streams for the big, like, landing of Perseverance and, like, the big, stuff like that. But I would imagine at least they have some sort of internal, little party kind of thing. Especially because, like, a lot of the PIs that work on these, like, they'll get their, like, one mission, and that's, like, their big thing that they work on for 10 or 15 years of their career, and, like, that's the thing. Oh, don't talk about Hubble dying. No. We gotta get James Webb in the sky first. Hubble will live forever. All right. Penetrating the murk of star formation. As we peer through the plane of the Milky Way, the center of our galaxy is completely hidden due to interstellar dust. The galactic center is 28,000 light-years away, and only 1 in a trillion optical photons can escape. It's like trying to look through a closed door. Unless this cold and grainy dust is accounted for, intrinsic stellar properties can be badly misjudged, a point first noted by Robert Trumpler in 1930. Star formation takes place in chaotic, dense, swirling regions of gas and dust, where the concentration of dust is so high, the action is mostly hidden from view. There's a dramatic difference, for instance, between the optical and infrared views of the Orion Nebula. In the optical view, the bright nebula contains a dark region that appears to be devoid of stars, while in the infrared view that penetrates the dust, a dense star cluster shows up in that dark region. The youngest stars are invisible even to the most powerful optical telescope. However, with Spitzer's ability to penetrate dust, the broad sweep of star formation in the Orion Nebula, M42, and the Omega Nebula, M17, and throughout the Milky Way has been revealed. Spitzer's detectors are so sensitive that the telescope has lifted the veil on some of the earliest star formation in the universe. Black holes that inhabit the centers of all galaxies are generally starved of fuel and are quiet. But it was not always this way. When the universe was 7% of its present age, nearly 13 billion years ago, it was 7 times hotter and 350 times denser than it is now. There was a furious phase of star formation and galactic construction in the first 3 billion years after the Big Bang, during which many of the largest galaxies were put together. Spitzer has 2 unique advantages for studying the distant universe. The first is associated with the redshift caused by expanding space. By the time the light from a galaxy 13 billion light years away reaches us, its light has been stretched and mostly shifted to the infrared. The second advantage is that light from star formation and black hole growth shrouded in dust in the early universe is absorbed and re-radiated at longer wavelengths where Spitzer works best. As a result, Spitzer has provided a more reliable measure of the star formation history of the entire universe. The most distant infrared luminous galaxies have a rate of star formation thousands of times larger than the Milky Way. Such a rate was sustained by the ready availability of gas in the denser primordial universe. Gas was consumed so quickly that the fireworks didn't last long. One provocative and tantalizing study claimed to use Spitzer to reveal the first objects produced by gravity in the universe, at the end of the cosmic dark ages. Alexander Koshlinsky and his group studied the diffuse infrared background in ultra-deep Spitzer images. They first carefully removed light from foreground stars and nearby galaxies, leaving only the most ancient diffuse radiation. Then they analyzed the fluctuations of the faint infrared emission that remained and matched them to simulations of clustering in the early universe. Quote, "Imagine trying to see fireworks at night from across a crowded city," explained Koshlinsky. "If you could turn off the city lights, you might get a glimpse of the fireworks. We have shut down the lights of the city to see the outlines of its first fireworks." End quote. It's unclear whether the faint infrared glow in Spitzer's ultra-deep images actually comes from a first generation of huge stars hundreds of times the mass of the Sun, or from the first wave of supermassive black holes. Either way, this truly ancient radiation carries information about the universe when it was a fraction of its present age. And there is a photo of that I will show you guys. Oh my god, that was so loud. Oh, was that really loud for you guys? Why is my audio so high? Oh my god. Sorry, that scared me so bad. Thank you so much though, Chazio. Thank you for subscribing. Oh my god, amazing. I'm glad it wasn't as loud for you guys. For some reason, my headphone audio was turned up like 50%, which is too loud for me. But thank you so much for that subscription. It surprised me in a good way. Welcome to the Teach Astronomy family. What was I doing? I was looking up an image for you guys. It is here. Okay, I gotta turn it. Hold on. We're getting there. We're getting there. I didn't have time to do my cropping this morning. Normally I make the images all nice before I get on here, but I was running late today. All right. Do I want to save a copy? No, just save it. Just save it. Just save it. That's fine. Okay. Great. I have an image for you now. Here we go. So this is it says the early phases of the evolution of the universe are probed in this very deep image from the Spitzer Space Telescope. After blanking out stars and galaxies, the uniform gray areas, there is a faint varying glow of infrared radiation. The pale to dark shading that represents structures in the universe that formed 13 billion years ago. So it's a little hard to see here, and honestly, it's not easier to see it in the book. I wonder if I can find a color image of this. Give me 1 second. I'm gonna try to look this up because it is a Spitzer picture, so. because it's like, it's not very clear. There's only so many. It's not going to tell me what it's looking at. Okay, that doesn't help. I guess we're just going to have to figure it out ourselves. I want to see what Spitzer saw. No, I don't want to see the telescope. I would like to see what it saw. This is frustrating. Okay, I don't know if I'm going to be able to find it. Damn. Okay. I will show you the other one then. But yeah, it's a little hard to see. But essentially these like splotchy things, all of these like splotchy dots, those are the galaxies that are being blocked out, that are really bright. And the researchers are looking at these areas where things are like the colors are more blended together and stuff, and that's the indication of like different levels of infrared radiation between galaxies and stuff, and between stars. So yeah, I was shook. Oh my god, maybe you're watching the Netflix preview. Oh, so true. If anybody has Netflix here, I think that's really the only streaming service that does it. As soon as you hover over a freaking anything on Netflix for more than 2 seconds, it screams at you. It screams the trailer at you, and it's so frightening. Talking about Hubble. Yeah, Hubble's great. NASA collaborated with SpaceX for a launch. India's going to launch another 3 or 4 special satellites and followed on with UAE, Canada, Egypt, and Iraq. Wow. Yeah, we got to talk about that on Wednesday, too. There's a bunch of stuff coming up. I know we talked about it earlier in the year, but it's always good to... in Brazil. Always good to see what's changed. Am I from New York? I'm from New Jersey, actually. Sometimes I joke around and do the Jersey accent sometimes. Your son's learning to color space images in his Intro to Astronomy college course. That sounds really cool. I never got to do that in my courses. That sounds fun. I took it to image some things. I imaged the Crab Nebula. I have that picture somewhere, but not on this computer. Maybe I'll show you guys that sometime. I got to image the Crab Nebula with a big telescope in Tucson. So that was cool. Alrighty. Let's continue. Closer to home, Spitzer conducted a sky survey of our own galaxy, dubbed GLIMPSE, the Galactic Legacy Infrared Mid-Plane Survey Extraordinaire. That's so funny. Sometimes NASA really wants a good name for something, and so they add just one extra word that makes no sense to be there. Why is extraordinaire in there? Because it needs to be GLIMPSE. So fun. Anyway, so it's dubbed GLIMPSE. By making images of swaths spanning 65 degrees on either side of the galactic center, and 1 degree on either side of the galactic plane. 100 times the sensitivity and 10 times the resolution of any previous survey, the GLIMPSE mosaic represents 110,000 different pointings of Spitzer, and 840,000 individual images, with the postage stamps painstakingly stitched together to make a seamless map. Spitzer's GLIMPSE photos are as scientifically meaningful as they are aesthetically stunning. But since Spitzer takes data at invisible wavelengths, there's no direct correspondence between its images and the colors of the rainbow. The filters Spitzer uses for the GLIMPSE mosaic are sensitive to thermal emissions from dust at temperatures from 30 Kelvin to 1600 Kelvin. In the maps, blue represents radiation typically coming from older stars. Green. I'm actually going to look up one of these maps because I want you to see them. Let me find that because I'm sure they'll be very pretty. And I think I should be able to find this one easier. Yes, here we go. Cool. I mean, it's not the... Wow, okay, that's tiny. Why is it so small? Let's try this one. No, I want the big picture, sir. Okay. Let's see the big one. Just show it to me. I'm sorry. Gonna have, there we go. Okay, I got it now. So this is glimpse. I think this is the main photo, and these are probably close-ups of different interesting things, but this is the main photograph, which is, and it's stitched together with, like it said, 840,000 individual images. So you guys can look at that for a moment while I let me actually make it a little bigger for you. Beautiful. All right. And I'm going to read about the colors and stuff. So, in the maps, blue represents radiation typically coming from older stars. Green colors trace stellar embryos by the emission of complex molecules called polycyclic aromatic hydrocarbons. On Earth, these molecules are found in car exhaust and barbecue grills, or anywhere carbon is incompletely burned. Red colors depict radiation from the youngest stars, still in their cool placental dust, as well as diffuse emission from graphite grains similar to tiny pieces of pencil lead. While no simple coding scheme can convey all the subtleties of the astrophysics of star formation, this three-color scheme is useful for researchers and armchair connoisseurs alike. Polycyclic aromatic hydrocarbons are too thinly dispersed for anyone to be able to savor their sooty aroma, but they're excited by ultraviolet radiation, so they map out newborn massive stars. New stars reside in bubbles or on the edge of green ridges carved out by stellar winds. Many of these stars die as supernovae, which further excite the diffuse gas. The young stars appear as yellow or red dots, some in tight knots where they form together. Others are more randomly sprinkled throughout the disk of the galaxy. Older stars register as blue in the combined image, and they're so abundant that they merge into a blue-white haze. It's such a pretty image. Yeah, as Parzival said, it's so pretty. Hello, Ananya. Hello, Raptor Thumbs. That's a fun... Look at your little dinosaur. Wow, that's adorable. That's so cute. Oh, Parzival, yeah. Parzival put the Discord link in there if you guys want to join. We have a really cool Discord. And yeah, it's a bunch of nerds talking about science and space. And it's great. So join us there. The dino is fitting. I love it. All right. Where was I? Okay. The Glimpse survey has contributed to new understanding of the morphology of our Milky Way galaxy. Teams working on the Glimpse images cataloged over 100 million stars and used them to trace out the Milky Way's spiral arms and stellar bar. Spitzer Project scientist Michael Werner reports that the survey, quote, strongly confirmed previous evidence that the Milky Way is a barred spiral galaxy, end quote. Prior to this survey and that of Hipparchus, it was believed that our galaxy had 4 spiral arms: Norma, Perseus, Sagittarius, and Scutum Centaurus. Adding its data to the Hipparchus survey, Glimpse confirms that the Milky Way has only 2 major arms, Scutum Centaurus and Perseus, that trail from the ends of the stellar bar at the galactic core. Additionally, as a result of Glimpse, astronomers have determined a new obscuration relationship for the galaxy, allowing more accurate estimates of distance to stars, even in the presence of dust. Most fundamentally, they've measured the pulse of the galaxy by counting how fast new stars are forming. Our galaxy generates, on average, 1 star like the Sun per year, using mostly recycled gas from the death of older stars. That doesn't sound like much for a system with several 100 billion stars, but as the Milky Way settles into the steady rhythm of middle age, its wild times of forming thousands of stars a year are long over. Oh, am I reading some sort of space mythology? No, I'm actually reading a nonfiction astronomy book called Dreams of Other Worlds. Yes, by as Parzival said, Dreams of Other Worlds by Professor Chris Impey and Holly Henry. There's an H there. Yeah, this is our little book reading chat thing. Professor Impey actually does Q&As here normally every couple of weeks. Now we're actually going to be moving to probably every month. This is one of his books. So this is all factual information. This is all that good science. And did you ever get the Holy Grail parcel? That's funny. But yeah, this is all that real stuff. All right. Given the volume of glimpse data, the public has been recruited via the website zooniverse.org to assist astronomers in analyzing Spitzer's views of our galaxy. Launched in 2007, Zooniverse developed the Milky Way project, by which citizen scientists scour Spitzer's glimpse images to identify gaseous nebula and newly forming stars. Zooniverse offers a variety of mission data sets to volunteers who assist in identifying new solar system formation, track ancient weather patterns, report solar storms, and hunt for massive explosions of stars called supernovae. For the Milky Way project, volunteers use simple online tools to circle huge bubbles of gas and dust in which stars are currently forming. The Glimpse survey imaged thousands of these globe-like bubbles where high-energy radiation from newborn stars collides with surrounding dust clouds. As the Milky Way project site explains, quote, "Right now our best understanding is that these are regions around young massive stars that are so bright that their light has caused a shock wave to affect the cloud around them and blown a bubble which we can see in infrared light." Raptor Thumbs, thank you so much for following. Welcome to the Teach Astronomy family. I will get to your comments in a second. Identifying massive bubbles in Spitzer's images assists scientists in determining the mechanisms occurring in star birth. Of course, it was always understood that the day would arrive when the last drop of Spitzer's 350 liters of liquid helium would evaporate away. This occurred on May 15th, 2009. Without liquid helium, the telescope's long wavelength instruments have lost all their sensitivity. However, the two shortest wavelength channels of one of the cameras can operate at their design sensitivity, so Spitzer was approved for a warm mission phase, where it is continuing to do important science. Even in its diminished state, Spitzer is more sensitive than any ground-based telescope in the infrared. Also, warm is a relative term. Touching any part of the spacecraft would give you a very serious cold burn. At the Balmier operating temperature of negative 242 degrees Celsius, Spitzer is continuing work with the two channels of one instrument as part of its warm mission. Given that its near-infrared channels are able to do science from comets to cosmology, more than 50,000 hours of programs have been approved since the warm mission started in 2009. Exoplanets are hot, so some of the largest programs were to characterize exoplanets where a line of sight is aligned with the orbital plane of the exoplanet. As the planet passes behind its parent star, the combined infrared emission from the star plus the exoplanet dips, and measurements made at different wavelengths, can give the size and temperature of the exoplanet. By the end of the mission, the number of exoplanets characterized will have increased from a dozen to 50 or 60, and will have a much better understanding of the extraordinary diversity of other worlds in space. To set the stage for this exciting Spitzer science, we take a detour into the role of light and darkness in the evolution of life. We can only imagine the flora and fauna that might possibly exist on planets orbiting other stars, but life's adaptation to light here on Earth might offer some scant clues. That's the end of that section. What are we looking at? Are you guys talking about Parzival's name? Got you. Oh, you're talking about the meaning of his name. Gotcha. You find space super fascinating. I'm glad. So do we here. That's why we started this channel. Have I played the game Outer Wilds? I have. Actually, I have played part of Outer Wilds. I've also played Outer Worlds, which is actually funny because they were talking about the Stellar Bar before, which is part of the Milky Way. And I pronounced it Stellar Bay because Stellar Bay is a place in Outer Worlds, which is funny. Little Freudian slip. But Outer Wilds is great. Yeah, I've only played a little bit of it, and I was actually thinking about possibly starting a little gaming series here on the weekends and playing Outer Wilds with you guys. It's a really, really... Yeah, I haven't finished it yet, so I thought it might be fun to maybe start a new save and play on Twitch if anyone would be interested in that. It's a great game. You would love to see me play. Oh, great. I'm glad there's one person. Yeah, it's a really cool game, and I thought it would be cool because for those who haven't tried it before, you get to explore space as this like alien race that it's very pioneer-esque space kind of thing. Everything's like built out of like wood and kind of like shambly, and like going to space is a very, I wouldn't say routine thing, but like it's almost like a, you know, we're gonna go explore out on the prairie, so we're just, and like going into space is just like that. It's very cool. It's a very cool game. Really beautiful, and you get to like pick where you go and stuff like that. So I thought with like input from chat, it would be really interesting. I heard the ending's really good. Yeah, so that's something I'm thinking about doing. What else is going on? I think that's it. All right, we shall continue. Are you playing Subnautica at the moment? I have a friend who, he was actually part of the Active Galactic group a while ago, and I believe might be rejoining soon. His name is Grant Bowman, and he actually has a YouTube channel where he plays Subnautica. He's a writer, and so he plays the game, and then at the end of the game he does a special stream or video where he talks about the storytelling and like how it's interesting and cool. He's a cool guy. He got the stream on a speaker in the background. Nice. Yeah, enjoy it. What am I sipping on? I have a I think it's a raspberry. Yeah, it's raspberry. Wasn't sure if it was raspberry or blueberry, but raspberry matcha tea. Cyberpunk 2077. I haven't tried it yet. I have a friend who I share a game library with who owns it, and I haven't tried it yet because, you know, everybody just T-poses all over the place, and I can't handle it. It's so funny. But I need to try it soon. It's green because it's matcha tea, so it's like it's a green powder tea with some raspberry flavoring. That's why. You came to the stream because it reminded you of Outer Wilds. That's crazy. Oh yeah, Dreams of Other Worlds, Outer Wilds. Yeah. There you go. Any plans for Mass Effect? I have not played Mass Effect. Should I play Mass Effect? I don't know. I feel like I love video games. I really do. And I'm good at video games. As far as combat goes, I'm good at video games that like the only thing is combat, like Overwatch or like Call of Duty, stuff like that, where like the main thing is like you're gonna shoot somebody. However, things like Fallout or like RPGs kind of things like that, where like half the time you're running around and like talking to NPCs and things and like revealing story, and the other half the time some creature is attacking you. Ooh, it's rough. I do need to start some special streams for subs. Maybe, I don't know if people would be interested in watching gaming streams as sub-only streams. I don't know if enough people would be interested, but we do need to do more special streams for subs. I'm working on that. Also, we're definitely going to do something special once we get to 1,000 followers. So if you are watching right now and you haven't followed yet, which I think a lot of you already followed, but make sure you follow, because I I don't know what we're going to do, but it's going to be something big because 1,000 followers is a lot. All right, I'm going to continue. We've got a couple more pages left, and then we can chit chat for a little while if you guys want to hang out. Stars, life, and sight. Exoplanets have quickly become the focus in the search for life beyond Earth and the quest to know whether we are alone in the unfathomable depths of space. Finding a large number of habitable exoplanets would suggest that life abounds in the universe. For now, astronomers are scouring stars in the Milky Way most likely to host habitable worlds. Stars range in size from small, cool dwarfs no bigger than Jupiter to colossal stars topping out at about 200 solar masses and 10 million times brighter than our sun. Blue giant stars are very hot, bright suns, such as those in the Pleiades cluster or in Orion's belt, that emit mostly UV light. About half of all stars are binaries, in which one star orbits another. Binary star systems can host planets with stable orbits around both stars, called circumbinary planets. The first of such exotic exoplanets, reported in 2011, was dubbed the Tatooine planet for its dual sunsets as depicted in the film Star Wars. But in some binary systems, gas interactions between the stars produce intense X-ray radiation, deadly to life on their attendant planets. The most common stars in the Milky Way galaxy are M-dwarfs. With less than half the mass of our sun, M-dwarfs emit most of their light at infrared wavelengths. Brown dwarfs, too small to generate nuclear fusion in their core, emit light solely in infrared. Among the many types of stars, it seems we couldn't have wished for a better star to orbit, nor one more suited for life than our sun. And there's a figure. And by figure, I mean just a... Oh, did I disappear there for a second? I don't know if I did. I don't think so. Just a cool picture that I will show you. Uh-oh, where'd it go? Oh, gosh. That's not it. There it is. Okay. Here we go. So this is an artistic rendering of exoplanet Kepler 16b that orbits a double star system and experiences dual sunsets as on Tatooine in George Lucas's Star Wars. The exoplanet has roughly the mass of Saturn and orbits the twin stars about twice a year. Astronomers were surprised that planets could form around a binary star. So that is, if you guys have watched Star Wars, which I imagine a good amount of you probably have, you have probably seen the great scene with Luke Skywalker looking out over a sunset of two suns. And that's what it would look like from a planet that is orbiting binary stars. If anyone was there to see it, because like the book said, that they sometimes are a little dangerous. Oh, is that Ingenuity's first flight? Thank you for sharing that, Astro Kiriani. Yeah, we're going to definitely talk about that on Wednesday. And we can raid NASA's stream after this. Absolutely. That sounds great. All right. Any type of star can host planets, but the light stars pump out determines whether and what kind of life might survive on their satellite worlds. Astronomers Ray Wollstonecraft and John Raven contend that life works most efficiently with blue light, which they argue triggered photosynthesis on Earth. If that's true, one might assume that planets orbiting hot blue stars would be the most likely to host organisms. However, large blue stars emit dangerous ultraviolet radiation and expend their fuel in a mere 10 to 20 million years. By contrast, our sun has existed for 4.5 billion years, and astronomers expect the sun will not expend its fuel for another 4 billion. It's our sun's long lifespan, in part, that allowed time for photosynthesizing organisms to emerge. As it happens, our sun is the type of main sequence star that emits its greatest amount of radiation in the range of visible light. At some point 3 billion years ago, living organisms began to harness this light for processes in photosynthesis. Cyanobacteria, or its progenitor, began to use sunlight and carbon dioxide to generate food in the form of sugars, and in turn release a tiny gulp of oxygen. That seemingly simple development slowly but radically began to alter the chemistry of Earth's atmosphere, from one conductive to anaerobic life to an atmosphere rich in oxygen. But oxygen levels sufficient to sustain complex life as we know it didn't evolve until approximately 550 million years ago. As Leslie Mullen reports, quote, "If the evolution of photosynthesis is the same everywhere, then the lifetime of blue stars is just not long enough," end quote, for life to emerge on surrounding planets. Though no one knows for sure exactly how life emerged, a group of scientists at the Santa Fe Institute posit that the reductive Krebs cycle may have brought together chains of carbon molecules to produce the first organisms. The Krebs cycle, or citric acid cycle, describes how organisms produce energy by breaking down carbohydrates, fats, and proteins. In what has been called the metabolism first theory, the reductive Krebs cycle is proposed as the mechanism through which the first organisms emerged. Quote, "In some primitive single-celled organisms, the Krebs cycle operates in reverse. It takes in energy and puts small molecules together into big ones. Scientists term the reactions in this mode as the reductive Krebs cycle." End quote. Eric Smith, a professor at the Santa Fe Institute, has argued that geochemical processes on the early Earth, might have combined smaller molecules into larger ones because it was energetically favorable to do so, similar to the chemical reactions in the reductive Krebs cycle. In other words, life might be built into or be an expected outcome of terrestrial geology. Plants stretch their stems and leaves towards the sun, and even the earliest organisms would have used a single photon of light for fuel and to obtain valuable information about the immediate environment. Quote, "The very pigments that led to photosynthesis probably also allowed those earliest creatures to react to light," end quote, writes Ben Bova, who notes that even, quote, "single-celled organisms have light receptors, sensitive spots of pigment that absorb light," end quote. Michael Sobel's book, Light, Michael Gross's Light and Life, and Bova's The Story of Light explore the myriad ways life on Earth is enabled by, and is adapted to, the light of our sun. Photoreceptor cells in bacteria, plants, and animals demonstrate the selective pressure of visible light. As such, cells evolved due to the survival advantage they provided organisms on a planet with a star that emitted its greatest radiation in visible light. Quote, "The very earliest creatures certainly did not have a sense of vision," notes Bova. "All they could do was react to light the way a scrap of paper reacts to a puff of wind, move either toward the light or away from it." End quote. By the Precambrian period, soft-bodied marine animals emerged that had at least a rudimentary sense of light and darkness. Under such conditions, finding prey and avoiding being eaten were difficult prospects. But life on Earth would suddenly, on geological timescales, change. Neurobiologists Michael Land and zoologist Dan Eric Nilsson note that, quote, "Something remarkable seems to have happened in the interface between the Precambrian and the Cambrian eras. Within less than 5 million years, a rich fauna of macroscopic animals evolved, and many of them had large eyes," end quote. Land and Nilsson posit that a simple strip of photoreceptive cells in organisms could, in time, become curved to better sense the orientation of the incoming light. If that curved space became filled with a liquid, the light could be focused on a lens to create image-forming vision. Nilsson and Land conservatively estimate that the evolution of image-forming eyes could occur in 500,000 years, and perhaps as little as 300,000 to 400,000 years. Land and Nilsson, as well as zoologist Andrew Parker, have researched how eyes may have emerged in response to the light produced by our sun. The first sophisticated eyes, dating to 530 million years ago, appeared at the beginning of the Cambrian period, and they're evident in the extraordinarily well-preserved fossils of the Canadian Burgess Shale. Parker refers to the Cambrian as the Big Bang in evolution. Quote, "It paved the way for the emergence of the vast diversity of life found today, whether in Australia's Great Barrier Reef or Brazil's tropical rainforests. It involved a burst of creativity, like nothing before or since, in which the blueprints for the external parts of today's animals were mapped out. Animals with teeth and tentacles and claws and jaws suddenly appeared." End quote. Parker argues that visible light acted as a strong selection pressure for the development of eyes in most species. In what he calls the light switch theory, Parker contends that sunlight has been the primary factor in determining animal evolution, behavior, and morphology. With the emergence of more complex eyes, Cambrian species could colonize niches within the water column of ancient oceans that in turn impacted their morphology. Trilobites, for instance, thrived in Cambrian seas. There were some 4,000 species, and apparently were the first animals to develop compound eyes. The trilobite could clearly see its environment, navigate, and seek prey. As a result, they and many other species developed exoskeletons to protect themselves. Coincident with the evolution of eyes that could focus, Parker argues, the fossil record reveals the emergence of a radical diversity of all phyla of animals. Land and Nilsson agree, quote, "If eyes had not evolved, life on Earth would have come out very differently. More than any other organs, eyes have shaped the evolution of animals and ecosystems since the Cambrian explosion." And that's the end of that section. And I think we are going to end it there today. It was about half the chapter because it's a long one. What is this? We need to read this. It's amazing. Oh, that sounds really cool. If you don't like spiders, which I don't, read it in text mode because there's a picture of a bug. But the link that Parzival shared looks really cool. And and Esther Curiani also shared that Ingenuity flight that you guys should watch as well. And I think that's... Oh, sorry. Now I'm yawning. I think that's pretty much it for today. I hope you guys enjoyed that. We'll finish the rest of the chapter next week. And if you missed any from earlier today, this will be archived on Twitch, but I will also be putting it on YouTube like I have with the other chapter. So if you feel like listening to those, go for it. We will raid, yes. Before I do that, I don't think there are any other chit chats to wrap up, but yeah, what do we have coming up this week? On Wednesday, we have astronomy news, which, like I said, we are definitely going to be talking about Ingenuity's flight. That will be really exciting. On Friday, we've got amateur astronomy, where I don't know what we'll be talking about, but we'll be talking about something fun. Maybe the history of amateur astronomy. That sounds like a fun topic. I don't know. We'll see. We'll check it out. And I think that's it this week because I'm pretty sure Professor Impey is going to be switching to a every other week schedule for his Q&A sessions. So this week he has a Q&A on YouTube, and then next week will be no Q&A. The week after will be here, and then no Q&A, YouTube. So we're going back to our pre-COVID schedule, but also, switching between Twitch and YouTube. But yeah, space missions of different countries. Yeah, we can talk about that as well. Yeah, definitely. And I think that's pretty much it. So be sure to follow, and if you can, subscribe. Thank you again to Chazio for subscribing. Welcome to the family. And Raptor Thumbs for following. Am I missing anyone else? I don't think anyone else subscribed during our stream today. Yeah. And I guess that's it. Let's set up that raid. We will go raid NASA. Let me find them. NASA's just chatting. I think that's so funny. They're not even in the... Why are they not in the science and technology one? They're just chatting. That's really funny. All right, well, I will send you guys over there. I don't know when it's going to cut me off, so I guess I'll just keep talking. But have a great day, and enjoy the NASA stream. And you'll probably leave in just a second, and I'll see you later. Bye! Are you gone? I don't know. Yeah, you're gone, I think. I think it's... All right, enjoy NASA. Bye.